you, thank you, thank you, thank you. I might have to take that bit about the NSA off there, huh? Should I take that off? All right, well, thanks for coming. Looks like we lost a few, a little bit of a sparse crowd. People, it must be the third day, right? Third day con? People kind of tired, hurting? Yeah, yeah, and another 2 hours to recover afterwards, probably, depending on what you ate. For me, anyway. So I'm just going to jump right in. I got some fun stuff to give away. My company sends me out with these little things. I'm not even sure what to think of them, but it's a little bug stuck in a sucker, and it's kind of supposed to represent kind of the malware trapped in one of the technologies that we create at Bromium. So I won't say a lot about that, but I might throw one at you if I ask questions and you're brave enough to answer. I'll toss one, and I'll leave a whole bunch down here if you want some. I'm just going to leave them here because I got to get rid of them. So, does anybody know the name of the class I teach at Black Hat? Who's brave enough to say anything? Like, just say blah. Blah. He said it. Ah. Yeah. No, it's called Application Security for Hackers and Developers. And I go over fuzzing, source code auditing, reverse engineering, exploit development, stuff like that. So if you're thinking about taking a class at Black Hat this year, that's kind of one of the random trivia facts, I guess, about me. Does anybody have a guess where and when I gave my first talk at a conference? Just throw out a guess. I don't remember the number, but yeah, it was DEF CON years ago, probably 2005 or something like that. So a while ago, I guess. So anyway, enough about me. Although I would like to point out, I'm going to use my laser pointer, somebody special in the back row, way back there. I actually got my wife to come and listen to me. This is the first time she's come and listening to a talk that I've done. So yay, give it up for my wife. I told her I would try and embarrass her, you know. Because even though I'm a security researcher, how many of you know if you work in technology, you end up as somebody's like personal printer repairman or something like that? That's kind of what I am in the house at home. My wife says, I can't get the computer to print or whatever, and then I'm like, I don't know what's going on. What'd you do to me? It worked for me. I was fine, but and now it's not. So anyway, yeah, I'm sure you guys have had that issue or that joy. But anyway, give you a little background on this project. 2012, Microsoft did a contest called the Blue Hat Prize Contest. How many people heard about that? Anybody hear about that? A few of you heard about that. And I decided to enter that. I thought it would be fun to kind of do something in the defensive space because the idea with the contest was whoever could come up with the best, you know, like memory corruption, exploit prevention sort of technology. Basically, how to stop ROP was kind of really what I think they were trying to get, and that's what my protection was. So I submitted an idea to Microsoft on you know, like a technological idea with a proof of concept and some code and a paper and stuff explaining how I would, you know, make tweaks to the operating system to stop this hacker exploit known as ROP, which stands for Return-Oriented Programming. And mine actually, I got selected as one of the 3 finalists. And they wouldn't tell you, though, if you were like first place, second place, third place. And it kind of made a big difference because the first place winner got a nice prize, and the third place winner, which is what I ended up as, got a prize, but it wasn't a very good prize. But anyway, it was still fun to be a part of that and be it, you know, they flew us all to Vegas and everything like that and announced who the winner was a couple years back. So anyway, long story short, the reason I give you that background is the second place winner, his ideas are what mostly made it into EMET as far as the 5 ROP protections. So EMET does 2 things, 3 really, but a couple I'll talk about. And part of it basically tries to, so if you install like EMET on an older like XP box, it kind of brings the XP box up to sort of Win 7 standards by forcing ASLR and DEP on older processes that may not have it, that weren't compiled with it or whatever. So that's wonderful. This talk is not an EMET bashing talk, by the way. I did come up with ways to bypass all their protections, but I still think it's a free tool. So I'm not like down on it or anything like that. So don't take that away from this talk. That's not what I'm here talking about. I'm not trying to say that it's bad or anything. It's great, but you know, like any of and I'll explain why it has certain architectural limitations. But anyway, besides, so there's 12 total protections in ROP and in EMET, and 5 of them are specific to ROP. These ones, I think on the end, this MemProt, color, stack, whatever. I can't even read it. It's so small. You guys probably can't read it from the back. But I'll go over each one of those 5 basically and how to bypass each one. But I kind of started this project as sort of like, well, my idea didn't make it into the tool, so I wonder how hard it would be to beat up, you know, the second place winner's idea that made it into the tool. So I kind of had a personal motivation to sort of beat up on this a little bit, kind of as sort of a, maybe you should have picked me if it's first place. I don't know. I had fun with it. I kind of had a little bit of fun with that. So, but you know, to do the right thing, so I did this project in November of 2013 and gave the results to Microsoft at the start of the year, or in December really, of 2013. So they had like 3 months to try to upgrade EMET before I started talking about this publicly around RSA time in February. So did the right thing in terms of responsible disclosure and everything like that. So that I think is good and worked well. They were fine to work with, and so that was good. And they did actually make some changes based on this research, by the way. I'll talk about that. They released a 5.0 tech preview at the same time I started talking about it at RSA to kind of like coordinate that release or whatever. So to kind of start the project, I said, all right, let me try Metasploit, which is, you know, as you guys know, they're like the main pen testers framework or whatever, mainly because it's free and stuff like that. And just start by, if I have a vulnerable machine and I have a working exploit, it works. Okay, so I started with that. So the starting assumption is, and I have a working exploit that actually works. But then I installed EMET, and now it doesn't work. So that's kind of my focus is not necessarily on writing the new exploit or finding a new bug or whatever to exploit. It's more upgrading a working exploit to also bypass EMET. That was the focus. Okay, and so this little guy, he's sad. Orange is the color of my company. It's my company color, so everything's kind of orange just to follow that theme. But when I tried the standard Metasploit payloads, EMET blocks those for a couple main reasons. First of all, the browser exploits that are in Metasploit aren't very good because they kind of depend on like older techniques to bypass ASLR and DEP. Like they depend on a DLL that's at a fixed location that wasn't compiled with ASLR or DEP. So they essentially cheat to bypass ASLR. So all you really have to do is force ASLR, and it breaks kind of the free exploits as it is anyway. So, but even if that weren't the case, EMET would still stop the ROP-based exploits because of those special 5 ROP mitigations that are inside of it. So to be clear, even though I found ways to upgrade an exploit to bypass EMET, EMET stops like 98% of everything that's out there because all the sort of public domain exploits have kind of well-known techniques in terms of how they do their ROP and stuff, and EMET was kind of built with that in mind. So it sort of shuts those down cold, right? So that's good, although it was sad for me because I was trying to bypass it. So if you find yourself making PowerPoints instead of writing code, you got to try to come up with funny pictures. I know they're not very funny, but it amused me when I was writing this. So the 5 key ROP mitigations is what we'll talk about. And as I already stated, the assumption is that we have a good bug. And what I do when I was first trying to bypass each one of the 5 is I kind of bypassed them each in sort of isolation with contrived toy programs. So I use this MSVCR71.dll as my fixed DLL that was at a known location, so I didn't have to worry about ASLR. I was just trying to bypass the ROP mitigations. So I kind of cheated in my contrived programs, and then later, for the real-world example at the end, I dynamically find the base address of NTDLL and create a ROP chain and everything like that, which I'll explain those terms, I guess, in a second real quick. I don't have time to talk about 10 years of exploit history, and kind of go into all of it, but I'll explain the StackPivot and gadget and ROP chain and stuff real quick in just a second. So the first of the 5 ROP mitigations is called caller, and what that does is basically when certain key or critical APIs, which are functions that the operating system provides, are called, and there's about 50 of them, and that's configurable, that Microsoft has deemed as these are sort of critical. When those are called, then certain things are checked, okay? And so even as I get into the technical bits and bytes of the talk, if you don't understand anything that I'm talking about, you can at least understand from a high level that there's kind of two main problems with the protection in general. I mean, it has a lot of benefits and pros and cons too, like it's quick and it's fast and installs on old stuff that you don't have to recompile. It's got a lot of benefits, but it's got some drawbacks, and two of those are the fact that really EMET is basically just a DLL that is injected into a running process, okay? And an exploit is code that's injected into a running process. So they're competing on level ground, right? So architecturally, this defense, you know, you don't need a kernel exploit to get out of it. You don't need a hypervisor exploit to break out of a virtual machine. You're basically competing on level ground. So that's not really ideal in terms of an architecturally sound protection, if you understand what I'm talking about. But you know, it's better, certainly better than nothing. So that's one problem. And the other problem with with the second place winners ideas that got put into EMET is they don't actually stop ROP. They basically are heuristic checks at key points. So the analogy I kind of use throughout my talk is, imagine you're kind of, you know, you're going into a country, you're driving from Jordan to Israel or something like that, and you got all kind of contraband in your car, and as soon as you hit the border check, you just got to like stash it all, you know, because you're about to get checked. That's what's going to happen. You're about to get checked when you hit a certain key API. But then before or after that, you can break it all back out and be doing whatever you're doing in the car, okay? So that's kind of my sort of non-techie analogy. It was the best I could come up with. I'm not really an analogy wizard, but that was something I try to come up with to explain kind of how this caller check works, okay? And I'll talk about it more. But first I wanted to show, you probably can't read that real well in the back. If you go to our technical blog, labs.bromium.com, you can download the whole white paper that goes into more of the code if you want to kind of dig into the bits and bytes more than I'll have time to too. So you can kind of, and you can see a lot of other great technical stuff that we blogged about as well. This is just one thing that we blogged about over the past a year and a half or whatever. So anyway, this is just giving you kind of a picture of a typical ROP chain. So ROP, I've been talking a lot about that, return-oriented programming. Basically what that is that's kind of a code reuse attack that became popular when DEP became popular, right? So in the old days of exploitation, all you had to do was inject some shellcode on the stack and jump directly to it, and you could execute your shellcode right on the stack or the heap or wherever you were. And then operating system maintainers, security type people thought, well, you know, if we can just mark each memory page as appropriately, in other words, if a page only needs to be read-write, why is it marked read-write executable? Let's remove the executable bit and just mark that page as read-write. Then that prevents this whole category of injecting and running code from a particular page of memory where it shouldn't be, okay? And so then people, because it's this cat and mouse game, right, with exploit and defense. So then the attacker said, well, we'll just find a way to disable or re-enable the execute bit on that page or whatever, and that's kind of born the whole code reuse ROP thing. And that's basically what a ROP chain does, is each one of these D words, so this is meant for 32-bit code because EMET doesn't really protect 64-bit code. The 5 ROP checks are basically for 32-bit code only, so that the work I did was 32-bit. So I wrote this in Python. You can see my ROP gadgets equal quote, quote, so just starting a string in Python, and then I do ROP gadgets plus equal struct.pack less than L, and then a D word. So does anybody know what struct.pack does? Any coders in here? Any nerd? Yes. See if he's ready. Oh, bad throw. It what?
It creates a string, a sequence of bytes based on your input. It allows you to do a byte manipulation.
Yeah, so you're taking this D word. I guess the less than L is kind of the key of what struct.pack does. Does anybody know what the less than L does? Somebody way back there. I don't know if I can throw that far. Oh, that was money. Come on. That was a good throw. Let's call that like it is. Right, so that's the key. So I want to read my addresses left to right like you normally would read an address, but when you actually create a string, they need to go in reverse order. So like this, it needs to be like 8E, 72, 34, 7C or whatever. It needs to go in backwards to this whole blob that I'm creating, that I'm going to deliver to the vulnerable application, right? So you can use struct.pack, and that reverses the byte order. So that's all that does, simple little Python tricks. If you don't know Python, this is great. It makes it super easy to do this kind of stuff. So you've got this series of D words, And really what those are is those are addresses. So in normal execution land, your instruction pointer is moving forward, and your stack pointer is kind of up and down on the stack frame. Where in ROP world, what we're doing is we're returning to a series of D words or addresses. So your stack pointer is like moving forward, like your instruction pointer normally would, and your instruction pointer is kind of all over the place, hitting the end of the tail of all these functions. So it's like push, push, ret, pop, pop, ret, blah, blah, ret, blah, blah, ret. You're hitting all these things in retting, which when you return, you basically pop the next D word off the stack and you move forward. So that's kind of how, and what you do, the whole point of the ROP chain is to basically remark the page that you're on as executable, and then you run your normal standard Metasploit payload or whatever. So that's kind of how, if you don't know, if you've heard this term and nobody took the time to take 3 seconds to explain it to you, hopefully I just did, and hopefully that made sense. So a few terms, ROP exploit, gadget, where'd my thing go? And then gadget chain. And then one other thing is called a StackPivot. Does anybody know what a StackPivot is? That's the thing you do right before you run your ROP chain. Anybody heard of a StackPivot? Any brave soul want to take a guess at what it means? No brave souls on StackPivot. So if your stack pointer is going to be hitting each one of these D words as you ret, the first thing you need to do is you need to readjust your stack pointer so that it points to this input. Because normally your stack pointer is like in the stack somewhere. And if your malicious input is this ROP chain and that happens to be on the heap, you basically need to pivot the pointer, the stack pointer, to the heap first, and then you run your ROP chain, and then you run your shellcode. So there's kind of like 3 steps to that process. That's called a StackPivot. So anywho, this 7C address is basically going to call like virtual alloc or virtual protect or some protected critical API that Emmett's going to be watching, because that is the critical thing that's going to remark, change the page permissions, okay? That's the naughty thing we're about to do, is call that. But we can be doing whatever we want until we call that, and then we're going to get checked at that point, okay? And that's a ret to a jump. And so if you run that standard payload that I just did, you'll see that in your event viewer in Windows, you'll see something like when you tried to call kernel32.virtualalloc, Emmet busted this program, vulnprog.exe, via the caller check, which is the first of the 5 ROP mitigations that I'm talking about right now. Because the standard normal-looking ROP payload directly rets to some API that's watched. And directly retting to something that's watched is a known bad heuristic. So they're saying, oh, instead of calling this legitimately, somebody just tried to ret to this API or whatever. That's naughty. Busted. So you didn't get your contraband in your car put away quick enough, or whatever, however you want to think of that analogy. So in terms of bypassing, anybody have a thought where I'm going with this slide before I finish my thought? What's a way you can think about how might you bypass a protection like that? If you can't ret to this critical API, but you need to call it. I need to call this API, but they're kind of watching to make sure I'm not retting to it. What's that? Who said something? The eye of doom is coming to you. Yes? Maybe there's some indirection you could do and see how far back they check or something. That's a good idea. The idea I had was, well, I want to call virtual alloc, and like normal programs call virtual alloc, it has to work, because otherwise it would break every program that runs on your computer. So what if I just ret to a spot, this 7C blah, 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 59, what if I just ret to a place that already calls it legitimately? Like, that has to work. Otherwise, this program's going to fail. So that was my like bypass idea for this, is like, what if I just ret to this location? That's got to work. And it did. So all I did was I changed the ret to a call to this ret to a location that calls it legitimately, basically. It was just tweaked that a little bit. So I kind of stashed my contraband, hit the checkpoint, and everything's fine. So I sailed past the first ROP check. And then I thought, maybe this won't be so bad after all. Because I didn't know when I first started this how hard this was going to be. Is it going to take me months, weeks? I don't know. So then I got past that. And then the next of the 5 ROP checks is called SimExecFlow, which is like kind of a long, confusing name that basically does the same thing that the first one just did, but it does it on exit. So when you exit one of these critical APIs, it checks to make sure that you're going back to a location that legitimately called the API. And so at first I was like, man, this isn't even hitting. And then I realized, oh, I don't need to do anything extra to bypass this, because that has to work already because of the same reason that the first one has to work. I'm calling it from a legitimate location, so it's going to return to a legitimate location in code. And that location is basically just a long gadget. It called the API and it did some stuff and then it read it. So I just needed to make sure that whatever it did in the meantime didn't break anything. So that was, the only thing hard about that was it took me a while to figure out why I was already bypassing it. So I didn't have to do anything extra to bypass that. Okay, so now I have, quote unquote, my hex CC. So you definitely can't read it, but the instruction pointer is pointing to a heap page because I called virtual alloc instead of virtual protect. And I put one hex CC as my first thing to execute. Because this page, this heap page that I just allocated, I allocated it with read, write, execute. And you can see that probably can't read it, but I did a virtual protect to show bang vprot EIP to show that this page is marked with read, write, execute, which is what I need to execute legitimate shellcode. So what is a hex CC? Does anybody know? Why would I put that there? Any thoughts? Any coding weenies? A hex CC translates to an int3, which is basically a software breakpoint. So basically, when you're writing an exploit, you take it, you sort of build your exploit in stages just like you would software. So you don't try to build your whole exploit at once and put your shellcode in and do it all from the get-go because it'll break and you won't be able to debug why it's breaking. Is it because the shellcode's not working right or you're never getting to your shellcode or it gets kind of confusing. So if you start with just one CC at the very top where your shellcode would be, it stops right in the debugger and you can go, oh yeah, and you can check stuff, page permissions, and okay, now I can put in some real shellcode. So you kind of like develop it in stages, so to speak. All right, so anyway, so that's working. So the next of the 5 ROP protections is called LoadLibrary. And that would be something that you would want to check because a lot of exploit payloads may want to load some other library to do whatever it is they do. If they want to call out to the web or something like that, depending on what this malicious payload is doing, it may want to leverage existing code. So that seems like a good check to have to see if libraries are loading. The problem is libraries load all the time. So it can't really stop DLLs from kind of loading and unloading because that's a normal thing that processes do. So the only thing this check really does is it checks to make sure that DLLs aren't being loaded from a remote path, a UNC share path or remote situation. So, and you definitely don't need to do that in legit shellcode. So the only thing I did to bypass this was just make sure that my shellcode didn't do that. So that's kind of you really don't need to do anything, so to speak, to bypass this protection. Just don't do that. There was something else that messed me up called EAF, this address export filtering, and we'll talk about that later. That actually messed me up when I first tried my shellcode because I put in like a standard Metasploit shellcode where that hex CC was, and first of all, it died right here at this load library, and I thought, oh no, the load library check is working, and then I realized, no, that has nothing to do with it. Just when load library is being called, we're jumping to it instead of calling to it. So it was actually the caller check again. That very first of the 3 checks was messing me up there. So I changed that to a call instead of a jump, and I got my connect back shell. So you can see I ran my toy program to start with is called vulnprog.exe, and the Python code is generating this exploit.bin, and then I got my remote shell, and then when I typed exit, it actually crashed. EMET busted me with this EAF mitigation. It's one of the other, it's not one of the 5 ROP protections, it's like a 6th of the 12 total. It's one of the other protections. And we'll talk about what that is in a minute and how to bypass that. But for now, I thought, well, instead of using a standard Metasploit shellcode, I'll just write a custom shellcode, because that's one of the ways to get around these, is you can just write your own custom shellcode. Because what they do with this EAF is they're keying in on something that a lot of the shellcodes, the canned shellcodes do. They resolve functions by looking at the export table of the DLL. So you can just not do that as part of your shellcode. So you could write custom shellcodes. It's not really ideal though, because writing shellcodes is kind of a pain, right? It's better to just use the ones out of Metasploit. So we'll show in a second how you can bypass that and then use just a regular shellcode again, because writing your own is kind of a pain. But I wrote a little one here, and it's just a message box that pops up a little message saying something like, sorry, you've been pwned by labs.bromium.com. And as the title, it says, should have picked me as first place. Just kind of, I don't know, just to have fun with that. So that's all that custom shellcode does. And I keep kind of showing this. This is just the ROP chain. It's basically the same as it was, but I've changed a few things, a few of the addresses and stuff. And like I said, you can see the white paper to kind of look through all those to figure out what's going on there. So when I run vulnprone.exe with this exploit.bin, yep, my custom shellcode runs, which is fun. So that means I've gotten past the first 3 of the protections and one more, the EAF as well, by writing my own shellcode in that case. But okay, there's a couple more though. There's one called MemProt, and what this does is this basically makes sure that you don't use the API virtual protect. This is like a super naughty API that they like watch like a hawk, because this is the one that's used by most of the ROP payloads out there to change the page permissions of the current stack page to run a regular shellcode, okay? So if you're gonna use virtual protect to change the page permissions of a page on the stack, you'll get busted by this protection. So how to bypass that? Well, we could use virtual alloc and make a whole new page in the heap that it's read, write, execute. That's what I've been doing all along, because I just had a feeling that was going to be a better idea, because I know that's something that has to work, because a lot of programs do that. They need to allocate a new page somewhere, and they need to, like, for JIT type code, for JVMs and stuff like that, they need to be able to actually run code dynamically in a heap or something. So I kind of had a feeling that's going to be something that's tough for them to really stop all the time, because some programs may need to do that. Or maybe there's some other API that works just like virtual protect, but it's a quote-unquote deeper API. There's a notion of kind of lower level APIs, because a lot of APIs call another program function, which calls another function, which calls the real function that actually does what the top level API is doing. So it depends on kind of where they hook of that function call chain, okay? Or you could use virtual protect to change heap pages, just not the stack. So there's like a number of different ways you could get around this protection, okay? And I chose the first as well as the second in the real world example. So just to give you kind of a look at 2 different ways to do it. So we could just allocate a new page, or we can find a deeper level function they're not checking. Both of those ideas actually work. And then finally, the StackPivot. Okay, so what is this 5th ROP protection called the StackPivot? How does that work? Well, as I was explaining earlier, one of the common things you have to do before you run your ROP chain is you have to pivot the stack pointer, which is normally pointing to the stack. That's why it's called the stack pointer. And you change it to point to the heap or some other place that it should never point to. So what they do is when you call one of these critical APIs, they check to make sure that the stack pointer is indeed pointing to the stack. So what's a way we could get around that? Any thoughts? How could you like kind of game that system? And again, the key is the fact that when you call a critical API, the stack pointer needs to be pointing to the stack. Otherwise, it can be wherever it needs to be, wherever you want it to be, because they're not really stopping it altogether. They're just kind of checking it at key points, right? So my idea was, well, let's pivot then. So I can pivot. I can do that. They don't stop me from doing that. They just check it at certain key checkpoints. I can pivot to the heap. Then I can copy my whole bit that's on the heap to the stack. I can unpivot. And then I can call my critical API and do whatever I need to do, because then it'll be on the stack again when they check it, right? So I can do naughty stuff in between. I just got to stash the goods when we get to the checkpoint. It's that same sort of idea, I guess. Or if you've already got a stack exploit, it really doesn't matter, because your malicious input, your ROP chain will already be on the stack, so it's kind of a non-issue. But I'm assuming that that this check relates to stuff that comes in through the heap. So there's a couple different ways. It may or may not matter depending on where it comes in the first place. But so again, showing this ROP chain. There go all the suckers. Somebody has to come and get them, because I'm not taking them with me when I leave. Here's the ROP chain. Here's the pivot. Here's some other stuff I do. And then basically I just output a blob to a file in Python. That's all my exploit does right now. So it's just a simple little thing to kind of, and I cheat a little bit when I do this StackPivot protection. I directly write some assembly code which copies my stuff from the heap to the stack, and then from the stack to the virtually allocated page that I allocate. So I kind of cheat a little bit there, and I'll talk about what we have to do to not cheat later. And then this vulnprog heap.exe with this malicious input, this exploit.bin or whatever, then it works too. So I kind of wanted to make sure So what I did for my research was, as I was doing this project, is I through contrived problems, I made sure that I could come up with ideas and prove those ideas out with toy problems for each one of the 5 protections, right? And now I'm going to kind of put them all together in a real-world exploit. That's kind of how I wanted to do that. So you should wonder, yes, but those were all on contrived problems, right? Can you actually do it against a real world? So for the main event, EMET versus real exploit. I wanted some cool music, but I didn't have any, so I just kind of, do my own sound effects. So what do you need? You need a real exploit that really works. So, and I'm not in the business of, like dropping O-Day or anything like that. So this is not like O-Day or anything like that. But this is an exploit. Metasploit has one for it, CV 2012, whatever. It's an IE. It was current at the time when I was doing this work, but it's like a little older now. I guess it's a couple years old now. But and the Metasploit one wasn't very good at all because, again, it depends on a non-ASLR DLL for it to work. So I needed a better version of this exploit, which I got from a friend of mine named Peter. So I have then what I was saying at the beginning. I have a working exploit. I have a system that's vulnerable. I have, in this case, an unpatched machine. And then, so everything's fine. And then I install EMET. So ASLR and DEP are not part of the problem. We have that solve via our exploit to begin with. The problem is EMET, those 5 ROP checks, because I have to do a ROP chain to disable DEP to run my payload, okay? So the problem is bypassing these 5 things that I've been talking about. So maybe I'll need a hyperspace exploit. I don't know. I just thought that was a funny picture when I was like Googling for random pictures that related to bypass. This was the other picture I found for bypass, like some kind of a plumbing bypass. I found a heart bypass picture too, but it was kind of creepy, so I didn't put that one up there. Anyway, so we need to do, one of the main things we need to do is that whole StackPivot bypass thing that I was talking about, because this heap, the bug is actually a heap-based bug in IE. So the malicious input, our ROP chain, will be coming in on the heap. So I do have to do that whole, pivot to the heap, copy it to the stack, unpivot, and run it from the stack thing. I have to actually do that. And I can't cheat like I did before, because I cheated when I first did it a little bit by just writing some assembly to do that whole copying. So I actually have to find new gadgets for my chain that do the copying for me. And that's not very hard. So as part of the exploit, I already resolved the base address of NTDLL dynamically. So you'll see all the gadgets are an offset into NTDLL. So it's like when you see well, I'll just show you on the next one. You'll see that every gadget looks like make adder NTDLL base plus some offset. That's the address of the gadget of this DLL in memory, okay? And this is all HTML, JavaScript type code, right? Because this is a client-side browser exploit. So all you really have to do to copy from the heap to the stack is you just need what I call a pop copy gadget, which basically just pops whatever's, so first you pivot, so you're pointing to your malicious input, and then you load a D word into a register, and then you move your D word to some address. The square brackets EAX means at the location pointed to by EAX, and EAX happened to point to the stack. And then I increment 4 times, because I need to move the stack pointer forward 4 bytes, and then well, this is at the very end, I restore. And then you basically just do this a whole bunch of times. So for every one of my legitimate gadgets where I've tabbed in, like this is one of the gadgets that I actually need to run, I have to do 6 more gadgets to basically copy that gadget from the heap to the stack. I do that like a whole bunch of times. I push all these gadgets that I really need to run with my pre-ROP chain to get my actual ROP chain to run on the stack. So it does make a total attack size basically 6 times longer than it was to begin with having to do this, which in this case wasn't a problem. There was like arbitrary unlimited space, so it was no worries on that. What's my time check? How much time do I have? 15 minutes? Okay, cool. So that was no problem. And then the other thing was this EAF thing I was talking about. So like I said, a lot of shellcodes, what they do is they resolve other functions by looking at the export address of like NTDLL or kernel or there's various ways you could do it. But that's kind of the common way to do it. And what the EAF check does inside of EMET is it basically sets a hardware breakpoint on this table inside the DLL. And it says if anybody tries to read or write this address, then we'll know that they're trying to do this naughty thing, because this program should never touch it in this spot in this way. Okay, so it's kind of like, oh, don't touch me there. So that's kind of the whole. That's how they're checking for that. And it's a hardware breakpoint. And I thought, well, if they're checking it with a breakpoint, in terms of bypass, can't we just clear that breakpoint? I mean, that shouldn't be too hard to like write some code that clears all the existing breakpoints and then run our normal payload. So that's all I do. So I had to basically come up with this whole, what I call an EAF bypass stub. So like your real shellcode starts here, and it's however long it is. And that's something that you can just grab as a blob from Metasploit. And then you basically just stick this bit onto it. And it's compiled with NASM, right? So it doesn't look like this. It looks like a bunch of bytes when you compile it with NASM. But basically all it does is it calls this syscall, this NT set context thread. It looks like a lot of code, but it's not. It's just one call, and all the rest of it is setting up for this call so that it clears all the breakpoints that exist in memory currently. So that's all you had to do to bypass the EAF check. So that was not really that hard, actually. That was a lot easier than I thought it would be. I thought it was going to be really hard to bypass that one. So just add that stub. And oh yeah, to point out my earlier point, there is actually this NTDLL, NT Protect Virtual Memory is a lower level version of Virtual Protect, the higher level API that they check. And so Microsoft knew that this was an issue. They knew that they weren't watching this other function that they wanted to watch. And there's actually a check inside EMET called deep hooks, and you can check that, and then it will watch this too, but by default they don't. And the reason they didn't was for compatibility reasons. They were breaking stuff by watching this too. So they it wasn't that they were ignorant of the fact that this lowered the security by not watching this lower level version of that same call. It's just that they made a conscious design decision to not do that by default. And so now one of the things they've done based on our recommendations was in their 5.0 tech preview is they enabled deep hooks by default because that helps. So I feel like we made a difference in terms of pushing EMET to be a better product as part of this research, which is kind of a cool benefit of doing this. So anyway, that's how, in this case, instead of doing virtual alloc to allocate a new page that was read, write, execute, I just used this lower level version of Virtual Protect to remark the stack pages after I shuffled my stuff. So I didn't need to copy again from the stack to the heap. I just executed right on the stack then because of this. So various ways you could do that. So putting it all together, I know you guys are starting to fall asleep, but so how many have seen an exploit demo before? What do you do in every exploit demo? You just pop calc, right? That's all it does. It's no big deal. And I don't know why that became the kind of de facto exploit standard. So basically, to set up for a client-side exploit, all you'll see me do is you'll see me start a Python server, which is hosting the malicious page, and then we browse to it with Internet Explorer, and you'll see the calc pop up, which means the exploit worked. Then I'll install EMET, and then I'll do the same exploit, and then you'll see that it won't work, IE will actually crash, which it shouldn't. EMET should report, but sometimes it can't, because again, they're fighting on a level playing field, so depending on what's corrupted, it can't report correctly in every case. And then I'll run the upgraded version of the exploit, which then bypasses EMET. So that's all the demo does. Let's see if I can get it to play here. I wasn't brave enough to try it live, so I just made a video of it. So this is all the HTML. It's just a big, long, ugly HTML page, which is the exploit. So I host that by using the Python simple HTTP server, and it just basically hosts whatever's in that directory when you run that command in Python. Okay, so you've got a web server running, you run IE, and boom, pops calc. Okay, and then you see that calc is running under IE, which sort of proves that that was an actual exploit. I didn't just hit the calculator button or something. And then I close that out, because I mean that would be cool to cheat too, right? You just kind of, there's a little button on a lot of keyboards that pop up calc, so you could be like, look, I just ran an exploit, the calculator jumps up. I've actually done that before. You hit it with your elbow and you're like, whoa, my exploit just ran. Are you kidding me? And you're like, oh wait, no, never mind. So, all right, now, so all this is basically just installing EMET, and that takes a second. So I have to sing and dance or something while that works. And then you'll see me run it again. And like I said, this time IE will actually close or crash, which isn't really good because it means it didn't properly report in your logs that an exploit was attempted, but you were still protected, okay? And that's a good thing. So let me try it again here. I'll run the same exploit. And instead of popping calc, it crashes IE, which it should pop up the EMET box saying like EMET protected you with check number 4 or whatever like that. But like I said, depending on what's actually getting corrupted in heap space, it's not always able to do that because it's not like doing it from a kernel level or a hypervisor level or any architecturally higher point. It's in the same space. And then I run the upgraded exploit and get the calc again. So yay, everybody clap. We saw calculator. Okay, so oops. I have it, here it is. And if you pop it up with hex as the default, it's even more elite. And apparently I'm not that elite because mine came up as like decimal. Never mind. It's a bad joke. It's a dumb joke. Don't worry about that. Ignore what I just said. So summary, to get past caller and SimExec, don't directly ret to a checked API. Instead, you could call a legitimate version that exists already in code somewhere. That was the way I approached that. There's probably other ways too, right? So these are all heuristics. The problem with heuristics and detection and these kind of things is that you think of a clever idea, somebody else thinks of a clever idea that defeats your clever idea. There's nothing sound that's happening there. It's just kind of like it's back and forth. In terms of the load library protection, just don't use UNC pass. In terms of the StackPivot protection, just make sure that the stack pointer is on the stack at the time of the check. That's what I did. And then for the EAF check, I just disabled hardware breakpoints. So in conclusion, I tried to find some funny pictures that sort of wrap up this protection. But I don't know how funny they are. They're probably not very funny. OK, they were dumb. All right, so to wrap up, you know, they didn't really cure the cold, so to speak. They sort of try to treat the symptoms. And that's not necessarily a bad thing. I mean, it's a free tool that stops a lot of the existing exploits. So I'm not down on it. I'm just giving you the whole picture, right? Because sometimes if you look at all the CVs that come out for like the current O-Day, and you read what Microsoft says to do to mitigate it, they're like, before you can patch, if you can't patch right now, one thing you can do is install EMET, and that'll for sure stop it or whatever. And it's like, probably it will, although depending on whether or not, if they actually took the time to upgrade it, maybe not, right? So it's just, I'm more just like, you need to know. That's it. I'm not saying it's bad or anything like that. I'm just saying that you need to know it's at least possible. So that was really my only point. I wasn't trying to beat up on it or anything like that. Furthermore, there's other user land protection. So anytime somebody is going to start talking to you about an endpoint security solution, you need to know what layer does this run at. Is it a user land protection? Is it a kernel driver? Is it a hypervisor deal? What are we talking about? Because those are the three different things that are out there, and they all give you a different level of soundness depending on how they approached it. So these presumably have the same issues that EMET does, although I didn't look at these other technologies. These are all other user land level type protections that inject a DLL or whatever. So in terms of fixes, what we did, we suggested to Microsoft some fixes they could do for their 5.0 check preview is they could, you know, enable those deep hooks by default, maybe come up with some better EAF deal so it's not so easy to just like clear breakpoints. Maybe somehow check more than one call deep that you came from legitimate code in terms of the first two, and maybe try to expand those ROP mitigations to cover 64-bit as code as well instead of just the 32. And so they did actually enable deep hooks, so that was good. We got some progress there. They did a little bit with EAF, but I don't think they went far enough in terms of upgrading that. And they came up with this whole new thing, which didn't relate at all to the work we did. It was called ASR, which is super confusing because it sounds a lot like ASLR, which I've already been saying. So if I say ASR or ASLR, you don't even know what I'm talking about. But this is a whole different thing. ASLR is the whole randomization of DLLs, right? This is attack surface reduction, which is just a good idea in general, which is basically saying, like, do you really need Flash to run for Office documents? Because by default, it can. Flash can run inside of, like, Excel or something. And so they added this new bit to EMET to say that you can disable, you can kind of pick and choose and say, no, I don't want Flash to ever run in an Office document, which is probably a good idea in general. You probably don't need that. Maybe you do, but probably you can get away without needing that. And then that lowers, that cuts off a whole attack surface, right? So I think that's a good idea. So thanks to people that helped me out, my crew at BR Labs, some of the guys I work with. Thanks to the people at EMET, they were good to work with. I actually met with them when I was at the Blue Hat Conference. And then other people that have done research in this field about bypassing EMET. There's been some other people that have done some work in this field. And then Peter, of course, for giving me a better version of the IE exploit that I kind of needed for the real world example. So I don't know how much time we have, but if we have some time, I'll take however many questions, if we have questions, that we have time for. So does anybody have a thought or a question or some burning comment they'd just like to make? So the question was, have EMET bypasses been seen in the wild? And that's actually a good question. I mean, so I don't have a whole picture of the wild, right? I mean, obviously, so I can't really answer it, but I can say what has been seen, and there have been a few exploits lately that if EMET was installed, they would detect it and they would actually bail out and they would not try to run. So they didn't bypass it, but they acted differently if it was installed, which in that case was a good thing. So if you had EMET installed, you were sort of protected because the exploit was sort of scared of you in that case. So we went from not seeing that sort of thing to now the exploits maybe detect that Emmett's there and bail out if it is, to probably that's coming, is my guess that bypasses are kind of, because what happens is like all the good stuff happens for years before the stuff that bubbles down to the wild happens, right? So nation states and all the big boys in the field, so to speak, that are doing exploitation use stuff that you won't see for a couple of years. So they've probably been bypassing Emmett for like, who knows, 2 or 3 years or whatever. And that stuff eventually bubbles into sort of, exploit kits and Metasploit and things like that. And then eventually it bubbles out to kind of the crapware, right? The malware, the Eastern European scam malware types that are, sort of like targeted to outdated stuff. So it takes a while for these techniques to really bubble down to kind of the mass malware, I would say, just in my personal experience. But that's just kind of my opinion. So I would predict it's coming, and hopefully not just because of my research, but because it was probably coming anyway, right? Any other thoughts? Or yeah, go ahead back there. No, so like this wouldn't help you against Heartbleed at all, because Heartbleed was, to your point, a very different, Heartbleed is a very interesting bug because there's kind of 3 different categories, right? There's the memory corruption bugs that do a lot of stuff in memory, changing stack pointers and EIPs and all this kind of stuff to run a payload and everything like that. That's kind of the typical memory corruption exploitation. Emmet helps with that. And then there's, on the other side of the extreme, there's like this whole more social engineering, like just tricking people into running a Java applet or calling them up and asking them for their user and path. I mean, there's this whole thing that you just can't, it's hard to protect against, right, technologically. And then in the middle, there's stuff like Heartbleed, which was kind of a unique deal because it was actually a memory leak, right? So you sent a size that was bigger than what it was actually needed or whatever. So instead of getting back like 100 bytes, you got back like 3,000 bytes or whatever it is. I forget off the top of my head how much. So you weren't actually changing memory. You weren't changing the stack pointer or the instruction pointer or whatever. You were just kind of reading memory and getting it back. And based on that, you were able to get their certificate or their credentials or whatever, right? And I actually, just a little off topic, but if you go to our blog, labs.bromium.com, I did a whole little blog on why fuzzing or other AppSec techniques might have missed that bug during testing. Because ideally, that bug should have been caught during testing, like all bugs should be caught during testing, but bugs slip through for various reasons. And I had 2 thoughts on that in terms of why that bug slipped through, to sum up my blog entry basically. But the first thought was just the heartbeat extension is toward the end of the protocol. And so testers who are developing fuzzers and things like that, they can't retool their entire tool set every time somebody pushes new code to a code base, right? So that might have just not been tested. I mean, that could be part of it. Or the other thing is, it might not have been tested properly, because you can actually detect mem leaks if you enable something like in Windows it's called page heap, and basically what it does is it puts a unmapped page behind every allocation. So if you try to read out of the bounds of an allocation even by 1 byte, it'll page fault and crash the app basically. But heaps don't normally run like that. You have to intentionally enable that sort of debug heap when you do testing to have that behavior happen to catch those sort of bugs. So maybe, in my mind, there's either 2 reasons why they missed it. Maybe they just didn't test it, right, for one reason or the other, or they tested it, but they failed to test it properly, basically. So that's kind of a, I don't know if it's a little bit of a long-winded answer to your question, but go ahead. So I had a slide that mentioned some of the things. I don't know if I can find it again, but basically they didn't remediate all of them, because some of them you just can't. It's architecturally you can't fix some of those problems really very well. But they did do some stuff. I don't know if I can find the slide again. Go up. Where was it? This is the one that had, they did some stuff, like they enabled deep hooks by default, which wasn't on by default, and they did some stuff with EAF to make that a little better. Those were really the only 2 things they did. They didn't do anything, as far as I know, to remediate any of the other issues like calling legitimate code and some of the other things I talked about. It's tough to, because the problem is you can't break real programs. You can do all these sort of heuristics and things as long as you don't break stuff, but a lot of heuristics either A, break stuff, or B, they're too performance impactive. So you're kind of left with whatever's left, which are a bunch of good ideas, but not necessarily foolproof ideas. You know what I mean? So it's tough with a solution that's not architecturally sound. If you're protecting at the same level that somebody's attacking, there's only so much you can do.
The code release is very like bypassing the MSR asset. When you jump into libraries that weren't able to pull your shell code.
Yeah.
Very just reliable like that.
Yeah. Yeah, it's tough to protect against kind of completely. I think you had a question. Did you have a question?
What did Microsoft say in any of your communications with them when they're going to put EMET as a default in? And I know you have to download, you have to install it, you have to enable it, and I know that the reason they haven't done it thus far is because they want to preserve backwards compatibility with open code. But I mean, this type of stuff is so important, and in the tests that I do, I go and I talk to the administrators that have never heard of EMET.
Yeah, none of them have, right?
Never heard of
Right.
this important type of protection.
Much less rolled it out.
So has
Yeah.
Microsoft said anything when?
It's a good question. So his question is, why isn't EMET in Microsoft by default? Why make you go and download something, even though it's free and you can download and install and it's not super hard to install and stuff? Why make people do that? Why not just put it in the OS? And two answers to that. First of all, they sort of have to some extent. You know, if you look at the protections in 8.1 versus XP, a lot of the stuff like the force ASLR and the always DEP and all the stuff that EMET makes XP do is already there in 8.1. So some of it is making its way into the operating system. The 5 ROP checks have not made it in, I think, because of probably speed and compatibility. It's bound to break some app. So if you're going to install EMET, you definitely need to check to make sure that whatever business critical apps you have work fine with it installed, because some of the heuristics, to his point, that they do, it's like, well, why don't they do better heuristics if those didn't work? Well, because they can't in some cases. It may break stuff that does stupid stuff, like it wants to run code on the stack. Like, I don't know why a program would need to do that, but if you've got some legacy app that needs to do that, you can still enable EMET. You may have to just unselect that particular check. So that's one of the cool things about EMET is you can get it going, and if it's crashing a certain app, you can actually debug and figure out, oh, why is it crashing? Oh, it's crashing because of the MemProt check. Just let me disable that for blah.exe, and then it'll work for the other checks. So you're still getting some level of protection. So that's kind of why I think that, so yes, right here. Is this for Linux? No, this is just Windows. This is all, EMET's a Microsoft only tool. Those same ideas you could do in Linux with some other tool or protection or some program or something, but this is all Windows. Am I out of time? Yep, okay, I'm out of time. So thanks everyone, have a good time.